we will have Thibault presenting on a girl's best friend, nested sampling. No, I'm kidding. It's on a software called Diamonds.
Yeah.
It does nested sampling, okay? So I think without further ado, Thibault, you can start.
Okay, thank you for this nice introduction. So let's move on. So good afternoon to everyone. So today I'm gonna tell you about the Diamond software, so which is a Bayesian software, and Diamonds stands for high dimensional and multi-MOdal nested sampling. So it's been published for the first time in Astronomy and Astrophysics in 2014 by Enrico Corsaro and Joris de Reeder from the Leuven University. So, Diamonds is a C++11 code implementing nesting sampling. Okay, wait guys, because why it's not working. Okay, sorry about that. It's a C++11 code implementing nesting sampling with simultaneous ellipsoidal sampling for Bayesian inference problems. So a Bayesian inference problem is happening every time you want to fit a data set to extract some given information, which means to constrain or fit the parameter of a model and evaluate the statistical weight of the model. So my plan for my presentation will be the following. First, I will talk about generalities on diamonds. Then I will talk about some basics of Bayesian statistics, since diamonds is using Bayesian inference. Then I will give some insights on the nested sampling, and I will conclude on an example of calculation with diamonds. So let's move to the generalities on diamonds. So the characteristic of diamonds, what are they? Diamonds has a basic core publicly available, and it's a general software for any application involving Bayesian inference. It provides like the Bayesian evidence, which is essential for model comparisons problem as a Turing output. It is very powerful in identifying multiple degenerate solution, also in high dimension. Its code implementation is flexible and easy to upgrade. It has different types of prior distribution and likelihood function already provided, and it overtakes existing nested sampling Monte Carlo codes, like the multi-nest code, who is the ancestor of diamonds and was written in Fortran. So for those of you that don't know much about Bayesian and think it's something marginal, like from just so specialist, I would like to emphasize the fact here based on this graph from the ADS website, that from where you can see like the numbers of paper with the word Bayesian in the title from 1990 until 2019. So as you can see, there is clearly an exponential trend in the refereed and non-refereed papers published, which makes of Bayesian statistics in astrophysics a very hot topic to deal with. So let's move to the basics of Bayesian statistics, since it's used in diamonds. So when we are dealing with Bayesian statistics, there is like a central point that we cannot avoid. It's the Bayes theorem, which takes its name from Thomas Bayes, who invented it in the 18th century, based on probability and risk assessment. And it uses like concepts that it's important to be aware of. So the first concept is, of course, the concept of dataset, which gathers observations, not in D. And the purpose is to fit this dataset thanks to a model that we're going to test on the dataset. And this model has input parameters from theta 1 to theta k, noted key frame parameters, which together makes a parameter vector. And we can visualize the parameter space containing the solution of a given inference process as a k-dimensional box, as you can see here. So now that the basic notions have been presented, I'm going to switch to the real formula. So as you can see on the bottom right, this is like, I think it talks to everyone. It's the historical formula of the theorem of Bayes, where you can see that the probability of A knowing B to be true is equal to the probability of B knowing A to be true times probability of A being true divided by the total probability of B being true. So in our case, this is not this form that we use this form on the left. I'm gonna explain because it's important for the rest of this talk. So one of the main concept here is the likelihood function. So the likelihood function like takes into account the data set, and based on this data set, she will give an output with a variable theta that I've just said before, like the set of parameters, and depending on the set of parameters, will give an output, a number. And the higher will be this number, the more likely the set of parameters chosen for a model will be the best to fit our data. Another important concept is the notion of prior probability density function. So here, this is the probability like randomly guessed. It's called a priori guessed, but a given set of parameter theta will make the model best fit our data set. And all the purpose of Bayesian statistic is to correct this first guess, this first a priori, and to get what we call the posterior probability density function, which takes into account the data set. So as an output, we get this posterior PDF, which will give a new value for the probability that a given set of theta parameters will get the best fit of a model for the data. And the formula I use to do this is this one, so you can know what it means. And the term here is called the Bayesian evidence, and it's the total probability that the model fits our data sets for any kind of parameter set. Okay, there is another way, like a simple way to visualize the Bayes theorem is to consider like the multiplication of the Gaussian likelihood by a flat uniform distribution. And this will lead to a Gaussian posterior distribution whose normalization volume factor is the Bayesian evidence, here epsilon. Okay. So one of the main points in Bayesian statistics is to obtain what we call the marginalized posterior distributions. Why? Because the credible interval exists only in reference to a marginalization of the k-dimensional distribution. Marginalization means integrating all non-interesting information over, so leaving out only the hypothesis we are interested to test, which means the parameter we want to estimate. Marginalizing can be thought equivalently as averaging on all the available information to incorporate it into the final estimate. This allows taking into account the general properties of the distribution, for example, the asymmetry, the outliers, or the degeneracies. Okay, so that's it for the main concepts of Bayesian statistics. So as you can see, like we need in this type of problems to compute integrals, but we're going to face some problems because of the high dimensionality over integrals, like, and already like for k super strict to 3, like no more analytical solutions to the marginalization problems are to be found, and also for consequently for the Bayesian evidence. So we could think like, well, we could do numerical integration, but for dimensions higher than k equals 20, even numerical integration is not enough to approximate, because it's too approximating and it's too computationally demanding. And then we face another kind of problem, which is relating to sampling, that I will explain right now. So numerical sampling techniques are approximate by definition, and complex distribution are extremely difficult to sample. So sampling algorithm can get stuck into a local maximum and never be able to explore all the parameter space, like it would be the case for the bottom panel, which is an egg box distribution. And computational time and the number of samples required can become a big problem. So we need solutions, and the solutions are, there are three possibilities. Like the first one is the typical Monte Carlo methods, then the well-known and well-used Markov chains Monte Carlo and MCMC, and the one I'm dealing with in this presentation, the nested sampling Monte Carlo, NSMC. So I would like just to make a brief recap of Markov chains Monte Carlo to explain after why nested sampling is different. So Markov chain Monte Carlo, it's based on the random walk analogy to the Brownian motion in the parameter space to find maximum likelihood values. Each chain is characterized by step size and by the initial point. Accepting a new point is done if the likelihood is better than the previous one. And we repeat this process with another chain and many more until we sample enough the parameter space. But this method faces some problems. And the problem is in sampling distribution with multiple modes, which means like multiple maximas, like the egg box I've just shown to you. So we could say that the metropolis acting algorithm has improved this problem, but it can be adapted just up to k equals like 100, but with very critical configurations of chains. And it requires hundreds of chains running in parallel and typically on the order of millions of sampling points. And Bayesian evidence, the things we want here, is not computed in this type of process. So this is why in 2004, a researcher named Killing inventing what he called the nested sampling Monte Carlo. So all the power of this approach is that it converts by a variable change the integral on the evidence into a one-dimensional integral. So to do that, it introduced the concepts of prior volume or prior mass, which is actually the prior multiplied by the infinitesimal volume in the parameter space. And doing that, we get this integral that we are going to look for solving. So the purpose is this one, where you can see on the left the parameter space with two parameters. It's to use a constraint on the likelihood that we're going to modify it. And as we shrink our constraint to higher likelihoods, which corresponds to a smaller ISO likelihood counter, we also reduce the amount of prior volume that we're using. Hence, X is progressively reducing from 1 to 0. And the good thing is, like, if we can calculate Li for each xi, then the computation of the Bayesian evidence is straightforward. It's just a multiplication. using the rectangular row or the trapezoidal row. So now the question to ask ourselves is, how do we obtain X? Well, we sample randomly with Monte Carlo method from the prior probability density function. And the prior is known exactly because we set it a priori and can be sampled with high accuracy no matter how many dimensions are considered. This is obtained by sampling each free parameters according to its own prior probability density function. So initially we obtain like j different samples for each free parameters, which means j points drawn from the total prior distribution. Each of these points is called a live point because these points are moving through the nesting sampling in the parameter space, and they correspond to a set of coordinates, as I said, in the k-dimensional parameter space. So each set of coordinates, which I mean by live points, corresponds to a likelihood value, hence to a specific prior mass x. The initial sampling of live points will resemble the prior probability density function in each dimensions. And if the prior probability density function is uniform, which is our case in most of them, and in my case too, then the initial sampling will appear uniformly distributed over the entire parameter space, as shown in the box. Okay, so now let's dig a little bit into the detail of an iteration process of a nested sampling. So for each live point, you have to compute the likelihood value straightforward, and thus you obtain a j likelihood values. Then you take the worst likelihood point in the sample and you remove it from the sample. Then you store the likelihood value and the live point is removed. And finally, you draw a new live point that satisfies the new constraint. Well, the likelihood is superior to the worst likelihood. So there is another way of saying this, like as shown on the panel on the right. Each set of coordinates, like the live points, corresponds to a likelihood value, hence to a prior mass, as I said, x, that you can see around here. And the new live point is drawn within the new smaller region contained in a new ISO likelihood contour at higher likelihood values, as you can see in the top panel. And the process is repeated until we reach the maximum of a likelihood distribution. Okay, so in a nutshell, what are the advantages of a nested sampling algorithm? Well, distributions sample efficiently, like the distributions are sampled efficiently, and Bayesian evidence computation is very accurate. Typically, it requires like 100 times less sample than the thermodynamic integration tools to reach the same accuracy plus the error bars. The sampling method is insensitive to any phase change like in likelihood like it is in thermodynamic integration. And it can sample very well multi-MOdal distribution. So distribution with a lot of maximas. And the posterior probability values required for parameter estimations are a simple byproduct, as shown in this equation. So one of the remarkable example of performances with nested sampling is with the Rastriging's function, which has a highly multimodal distribution with the global maximums, as you can see around the green target. It's like a hex box which would be bent in the center to the top for here 2-parameter space with a logarithm of the likelihood. And the diamond code proves to be able to quickly recover the position of the global maximum of the distribution, which would be impossible with the Monte Carlo chain Markov, or would be very, very difficult. As you can see here, it takes only 10,648 samples to find the maximum of the likelihood function. So why is that? Well, a part of the answer lies in the way the parameter space is sampled, and it's sampled thanks to the simultaneous ellipsoidal sampling. So the ellipsoidal sampler is based on the cluster algorithm. And the cluster algorithm also identifies groups of points that are clustering around a common center of mass. During the nested sampling process, the algorithm checks how many clusters can be found and therefore computes a k-dimensional ellipsoid for each of them. The X-means clustering is a variation of the k-means clustering that treats cluster allocation in a different way. And approximate parameter space with sets of ellipsoids reduce the prior volume to draw from. And we can draw from an ellipsoid very rapidly and draw new points until we find one with a likelihood better than the constraint. So as I said, like throughout the nested sampling computation, we have ellipsoids. And these ellipsoids around clusters are going to change their sizes depending on how the points are taken in and taken out. And the enlargement fraction of the ellipsoids is a critical parameter in the nested sampling based on the simultaneous ellipsoid sampling. It depends on the number of free parameters of the fitting model and has to be tuned accordingly in order to be able to perform reliable samplings of a posterior probability distribution. The relation shown here was calibrated using a set of 150 independent computations for a peak bagging analysis in asteroseismology. So one of the remarkable results is computational efficiency of the diamond code, which is shown in terms of the number of nested iteration at the top, and like the number of nested iteration required to converge to a solution, and the corresponding computation time at the bottom, in this case referring to a 2.7 gigahertz single core computation and a data set coding for about 2000 data beans. So what we can see is that the computation time is like proportional to the number of parameters to the power 3, which in the case of 50 parameters, when we have like 1000 points from the start, leads to a 16 minutes computational time. Okay, so now I'm going to show you like a typical example of what I'm doing in my PhD research with the diamonds code. So what you can see here is actually an attempt to fit the background of the powered spectral density of a star from the TIC catalog. And to do it, I use a model with just 4 parameters. So as you can see, like if there is an initial sampling of a parameter, then the nesting sampling goes down. So I'm going to explain to you what all of this means. So NEIT here is the number of the current nested iteration. Then NCL, it's the number of clusters, and it will vary within the allowed range as the computation proceeds. Then the number of life points you choose to sample your parameter space. Then you have CPM, which is like the cumulated prior mass, which converges to 1 towards the end of the process. You have the ratio. So the ratio is the final termination condition. It's an important parameter to track for understanding how much is left to sample for the posterior probability distribution. When this number reaches the value of the termination factor given as an input, the computation will end and the result will be generated. Here we have log E and IG. which are the natural logarithm of the cumulated Bayesian evidence and the information gained from the previous iteration. And here we have a projection factor, which is here not used, set to 0, but uses the principal component analysis. Why? Because if you use it, like the computation will fasten, but you can lose information. So you don't use it all the time. You use it only if you have a very high signal to noise ratio. What you have here is like another part of the iteration, just to show you how the numbers are evolving. So you see that the CPS is like converging to 1. You see that the number of clusters is like moving like from 1 to 4 to 3, depending on how the sample is down. You can see that the logarithm of the evidence is like converging to 0, and the ratio is going down actually until it will reach 1. So here is another insight. So I use a model. So this model is written in C++, as you can see on the right. And in here, it has more parameters. It's another type of model, like more complicated, a 3RV model with 10 parameters. And what I have to do mandatory before to launch my code is to set my priors for these parameters. So they are done, like it's done uniformly, which each line corresponds to another line here, like the first line here corresponds to the first line here. And I set like intervals, like for example, the flight noise levels. I said, like as far as I know, my guess for this would be between 8 and 22, and I do for all the other ones. And then I launch the code, and the Bayesian like process with nested sampling is launched. So that at the end of my computation, I will have a total new set of range of my priors, which will tell me what are the best ones for my model to fit my my background of my power spectral density. Okay, so here you see the end of the computation. So as you can see, it can be very fast if you know what you're doing and your priors are good. And what I want to stress here is like the ratio. I will just give a little bit more insight about it. Actually, the ratio is only an estimate of how much evidence remains to be collected with respect to how much evidence has been collected already. So it's displayed by this curve you can see at the bottom, where the red curve is like the quantity of of evidence which has been like received, and the blue curve is the one. No, it's the contrary. Like the blue one is the one like the evidence you have collected, and the red one is the one you still have to collect. And when those both curves like cross each other, the ratio equals 1, and the code stops, and then it gives you what he found. So basically, I will finish on that about the sampling efficiencies. So before 2004, like the Monte Carlo methods in the purpose to do the sampling of a parameter space to do like integrations, like needed like around 1 million samples required. Then with the first Bayesian software written in Fortran in 2009 called NesteD, it dropped to approximately 20,000 like samples required. And when diamonds appeared, like it dropped again, this time like in C++, so below the 10,000 samples, to finally drops to 1,000 samples to actually reach exactly the same results. And so what I can say is like, I would encourage you to try these techniques if you haven't done it yet in your own research, if you want to feed data with some models, because it can really gain you a lot of time and like be very efficient. Thank you for your intention. Hello?
Oh, thank you, Thibault, for your very interesting talk. So now we are going to allow everyone to ask questions if they have.
Yeah.
So
Yeah.
if someone wants to talk.
Yeah, can I ask?
Yeah, sure, go ahead.
Sure. Hi, thanks. So
Yeah.
I have two questions. One of them you've already answered, but just want you to re-echo it. Why you think nested sampling MC is better than MCMC? You gave a reason, but
Well, it's better because like on the contrary of a Markov chain, like you do not like, let me show you. You do not like go through your parameter space like with a lot of lines in parallel, which requires a lot of computational power. You use clustering, and based on this clustering, you use like ellipsoids, and it's a faster and more efficient way to sample your parameter space. And why also it's more like interesting, it's because sorry, I'm just coming back to the slide. It's because scaling introduced like a change in variable. He introduced this concept of like the prior mass, where the calculus here is simplified, like it turns out like a one-dimensional like integral. And what your constraint, contrary to the Monte Carlo, is not on the space in the parameter, it's on the likelihood. For me, it's like the main point of the power of this technique. It's what I understood.
I think an additional, sorry,
Yeah.
can I just, an additional benefit of doing nested sampling as opposed to just an MCMC is the fact that you can actually, it is better at identifying multiple nodes in your distribution for multi-MOdal
indeed,
rather than an MCMC.
Yeah, because like as I showed, like since you can like sample like multi-MOdal with your ellipsoids, like you can like, for example, here like if you use like Markov chains, it would take you an infinity of time to sample this and find your maximum, as I said, because it would get stuck in the local maximums.
Okay, yeah, that's understandable. And since you're using diamonds, I wanted to ask, apart from peak bagging, because this is what the tool was designed for.
Yeah.
I've been hearing like a new routine has been added where someone can do stellar parameter approximation or optimization. Is this true?
Yeah, it's the famed software developed by Enrico Corsaro. But honestly, I cannot tell you much about it because the paper has not been published yet. I went to Italy to learn with him, but I'm not an expert enough with it. But yeah, it exists. It will be released soon, like the famed software from the same author, where everything will be automatized and for stellar parameter. Yeah.
Okay.
Estimation.
Yeah. Thank you.
So
I have a question.
Yeah, sure. Go ahead. Go ahead, Elkin. Yeah, you can talk.
I was wondering how does diamonds compare with other nested sampling algorithms like multi-nest or NesteD or NesteD? Is it faster, or in what sense is it? Do you know about this other one?
Well, honestly, no, I don't know about the former ones like multi-nest. The only thing that I know, and I think it explains it, is that, but I'm not sure, but it would be my explanation, is that diamonds is written in C++.
Oh, which would be faster than Python, yeah.
Yeah, and multi-nest was in Fortran, and yeah, if it's something is written in Python, yeah, I'm afraid it would take an eternity to do anything. Yeah.
Thibault, so just a small question that I had. So when you talked about clustering the points, you talked about X-means algorithm.
Yeah.
What is it? Do you have an idea?
Yeah, I can show you. let me let me see my notes because I was also baffled by this. Okay, do you know about the K one, the K
Yes.
clustering?
Yes.
Okay, okay, good. So let me read again. Where is it? Because okay, just let me like 1 second, please. Where is it? No, it's not here. When do I talk about it actually?
I think it's
Do you remember the slide?
you are a little bit further ahead. You are like 1 or 2 in that one. Yeah.
In that one, okay. So let
No,
me
you
see
passed.
my notes.
You passed it.
Oh, okay. Oh, okay. In this one.
Yeah, in this one.
Okay. So the definition is like X-mean clustering is a variation of K-means clustering that treats clusters allocations by repetitively attempting partition and keeping the optimal resultant splits until some criterion is reached. That's the definition. I don't know if it makes sense. It's what they say. I can check like because yeah, I mean if there are no drawings, like it's impossible to understand. Like I would recommend you to check on the internet, like you Google it. I
Okay.
found it quickly.
Okay.
Because it's very similar to the K-means, but we just add some
Some
additional steps and a criterion to stop it. From what I understood. Yeah.
Okay. Okay, thank you.
You're welcome. Okay. I see there are some messages. Okay, recorded.
So if there are not more questions for today, we are going to end here our meeting. As I said, I'm going to upload the talk to YouTube so that those that have missed it can see it. And
yeah, and Andre, you can put my name. Like I checked, like actually you can put it. Like I checked, but my name is all over Google, so it's meaningless to not put my name on YouTube.
Okay.
Yeah.
So
it's not gonna change anything.
We will meet again in June, and then we'll do a break over the summer, but more info is going to be sent to your email eventually.
Okay.